Chapter 4.4, the Fundamental Theorem of Calculus, Day 2, Mean Value Theorem for Integrals and the Average of a Function. Now, if you remember the mean value theorem for derivatives, what the mean value theorem for derivatives said, you have a function, you have the secant line. Somewhere in that integral, provided it's differential and continuous, the secant line and the tangent line will have the same slope. Well, the mean value theorem for integrals says we have a function, and an integral is finding the area. The mean value theorem for integrals says somewhere in that integral, there is a place where if I draw the rectangle I drew will have the same area as the area underneath the function. So there's somewhere, some point, at least once in that integral where that height calculates the area as a rectangle. So in other words, this portion above the rectangle is canceled by this portion below. Mathematically, we say there is a C such that f of C times b minus a equals the definite integral. And we use that, very useful, for finding the average of the function. We look at the mean value theorem from A to B. Right? So the rectangle, that gives us the total area underneath. If we divide by the width, we're going to find the average height. So divide both sides by b minus a, and we can get the average of the function. So we can now find the average of something that does not go at a constant rate. It varies. Right? So let's look at a couple examples. Right? Find the average value of f of x equals 3x squared minus 2x on interval from 1 to 4. So we'll graph it. It's a parabola. Should look something like this. Not saying it looks exactly like that. From 1 to 4, we can see it doesn't increase at a constant rate. It's some increasing, some decreasing. Well, first we're going to find the total of all those rectangles that we draw, those infinite rectangles. And we do that with the definite integral. And once we found the total of it, we divide by the width, b minus a, and that'll find the average. Just like finding the average of a set of numbers. You add them all up, divide by how many they are. Well, that's what we're doing. We're adding all the rectangles up, dividing by the width. So as we do this, we got 1/3, which is 1 divided by the width of our rectangle. We'll do our antiderivative, x cubed minus x squared. From 1 to 4, we'll plug in 4. 4 to the third is 64 minus 16. We'll plug in 1. 1 minus 1 is 0. 64 minus 16 is 48 thirds, which is 16. So the average value of our function is 16. So the height equals 16 would be the average height of that function. And again, that means that this region below here canceled by that region above. Now where that happens, you would have to set the function equal to 16 to figure that out. And that's precisely what we're being asked in this question. Find the average value of the function over the interval and all values of x where the average happens. So first, let's find the average. All right, we'll find the average. 1 over 3 minus 1 times the integral from 1 to 3 of, and I'm going to kind of distribute and work it out here. We'll distribute. We got 4x squared plus 4 all over x squared. So we got 4 plus 4x to the negative 2 with respect to x. All right, we'll do that. Keep our 1/2 from simplifying this. We'll take our antiderivative. Antiderivative of 4 is 4x. Antiderivative of 4x squared is 4x. We power up to negative 1. Divide by negative 1, so we get minus 4x. From 1 to 3. So we got 1/2. I'm going to rewrite it again. Easier for me to visualize it when I put it back into fractions. So we got 1/2. 4 times 3 is 12, minus 4/3. Stick in 1. 4 minus 4 is 0 again. And multiply by 1/2. We got 6 minus 1/2 times 4/3 is 2/3. So we got 5 1/3. The average of that function is 5 1/3. Some people might want to say 16/3. 16/3 might actually be easier for finishing this problem because this is just the average. Now what we want to do is find out where the average happens. All right, so we'll find out where the average happens. We'll take our 16/3 and we'll set it equal to the function. So let's get rid of all this extra stuff. And we'll take 16/3, set it equal to the function. 4x squared plus 4 over x squared. Again, I'm going to split this. 4 plus 4 over x squared equals 16/3. Solve for x. We'll subtract 4. I'm going to write that as 12/3 over here. So we got 4 over x squared equals 4/3. Looking at that, we can see that x squared equals 3. So x equals plus or minus the square root of 3. Pay attention to our interval. It can't be negative. So the average happens at the square root of 3. So the average is f of square root of 3 equals 16/3. Okay, here's another example of the same problem. Set it up the same way. 1 over 2 minus negative 1 times the integral from negative 1 to 2. 4x to the third minus 3x squared with respect to x. All right, we'll do our antiderivative. End up being 1/3, when we simplify this fraction, times x to the fourth minus x to the third. As we do these antiderivatives, remember, power up and divide. Our limits are negative 1 to 2. So we'll have 1/3. We'll plug in 2. 2 to the fourth is 16. 2 to the third is 8. Negative 1 to the fourth is 1 minus. Negative 1 to the third is negative 1, so that'll be plus 1. So that ends up being 2. So we got 16 minus 8 is 8 minus 2, which is 6/3 is 2. So the average value of this function is 2. And we find the total value, the area, divide by the width of the rectangles. Now we just need to figure out where it's equal to 2, and to do that, we set the function equal to 2. So here's our function again. going to set that equal to 2. Set our function 4x to the third minus 3x squared equal to 2. This may be a good calculator-based problem. I'm going to use the solving feature, and I like to graph these. I'm going to graph 4x to the third minus 3x squared. Set that equal to 2. As I take a look at my window, keep a look at my range, my limits that they gave me in the problem. Right? On my graph, as I graph this, those are my x values. So from -1 to 2. Now I'm looking for when it's equal to 2, so I don't need to have my y value be much far away from 2. As the window I got set right now, it looks 2 is going to be in there, so I'm just going to leave it. So I got my function, I got what it's going to be equal to, I got my window set. All right, I'm going to graph it. And I can see it's equal to 2 at this point. And to find that, this should be old school for some of you. We're going to do second trace and find the intersection, the 5th option. Now, since there's only one place to intersect, this is easy. You hit enter 3 times. The first curve, there's only 2 curves on there. The first curve is the one it selects initially. The second curve is the one it selects next. And since there's only one intersection, I can just hit enter again. If it intersected twice, I'd want to arrow closer to the intersection I wanted, and then I hit enter. And I can see my intersection, x equals 1.136, or I can say 1.136, or I can say f of 1.136 equals 2. All right? So in review, the mean value theorem for integrals, it says in this graph where I'm finding the area underneath the rectangle, or area underneath the curve, there's at least one spot where I can make a rectangle that equals the area of that curve, right? Where this portion above and this portion below cancel each other out. And I can use that, to find the average value of the function. First, I find the area of that full rectangle, and I divide by the base of the rectangle to find that average height.